Hello, space fans. Welcome to another one of our fantastic conversations with an astrophysicist. I am your host, Scott Lewis, and with me, as always, is Katie Mack, coming
Hello.
from Melbourne, Australia. How are you doing today, Katie?
I'm good. How are you doing?
Oh, if you just check Twitter, you'll see how I'm doing. So I just got back from a wonderful party with my friends at Jet Propulsion Laboratory, and we had a little too much fun, but in the most wholesome way possible. Like it was just good fun. We were playing board games and being nerds, so it
Okay.
was
All right.
it was a lot of fun. But
I'm not
hey,
judging you. It's cool.
it's okay. A lot of people are, but if you want to check out Scientific Scott on Twitter and like the entire feed. You'll just laugh because lots of funny pictures were being done, and I think some of them are watching. So hello, friends back in Pasadena. What we're doing tonight, as we did 2 weeks ago, is we are going to be digging into the amazing and interesting science that is dark matter. What is it? How does it work? Last week we did touch on a few topics, and so here, Katie, I'll have you kind of do a brief overview of what we talked about, and then we're
Okay.
going to be getting into wimps versus machos and how do we do direct detection and indirect detection. There's, so to figure out what's going on there. So let's
Right.
figure out, okay, what do we know so far? What did we go over last week to catch everybody up?
Okay. So last week we went over the what dark matter is broadly, which is that dark matter is a kind of matter. So by matter I mean something that has mass. Um, it's a kind of matter that is invisible. So we can't see it. We can't touch it. It's invisible because it doesn't seem to do electromagnetism. So if you touch something, the pushback that you feel is electromagnetism. It's the electrons in your hand pushing against the electrons in the other thing, and you're not really touching it, but you're like, you've got that repulsion thing going on.
Right.
And so that's
So
why you
the
can't
fundamental
pass
force
through
is
things.
it just doesn't
Yeah,
play with the one.
yeah. So dark matter does gravity.
Yeah.
That's why it's matter. It has mass, but it doesn't do electromagnetism. So if dark matter if you tried to touch dark matter, your hand would pass right through it. So that's like the sort of fundamental property of dark matter. And because it doesn't do electromagnetism, you can't touch it, you can't see it, because it doesn't do electromagnetic waves, which is light.
Right.
So it doesn't absorb light, it doesn't reflect light, it doesn't emit light. And because of this electromagnetism thing, it doesn't collide. So it's non-collisional, we call it. So it can pass through stuff. It can pass through itself, it can pass through other kinds of matter. But because it has gravity, it collects in clumps in the
Right.
universe.
Right.
And there are clumps of dark matter, sort of all galaxies seem to be embedded in clumps of dark matter, and like the structure of the universe is basically like the structure of like galaxies and clusters of galaxies and everything is sort of embedded in this web of dark matter.
Yes, the
Um,
cosmic web, which again, like
yes,
last time, I still it's one of my most favorite things to see visualizations of. Just watching these
yes,
tendrils of everything connected together.
yeah.
So
So yeah,
so with that, so we know that it's matter. It doesn't interact with light with electromagnetism, but
yeah,
it does affect things around it. So we went over a little bit about how we have detected it as far as some of the evidence for it. But
yeah,
there's a lot of there's a lot of talk about these wimps and machos, and I think first we should break down what those things are. So
yeah.
first, what's a wimp besides
Okay.
something that you call someone on the playground?
So actually, I'm gonna go in historical order and start with machos.
Oh, so
Um,
let's go back in time and
yeah.
with macho.
So when dark matter was first discovered, we knew that it had the form of it sort of encasing our galaxy. We knew that our galaxy was embedded in dark matter, in a halo. We call it a halo of dark matter. Actually, I'm
Hmm.
going to show you. I'm just going to quickly sort of show you a little uh, like drawing of what a halo of dark matter looks like.
Okay.
So this is okay. So it's not always really spherical like this, but basically, when I say halo, I mean sort of a roundish, spherical-ish blob in which galaxies and things exist. Okay, so that's when I say dark matter halo. So we knew that there was a halo of dark matter in in space, like surrounding our galaxy.
Right.
We didn't know what it was, and so we thought there were a bunch of different ideas for what it could be, and one of the ideas was that it was some kind of massive objects sort of orbiting around in the halo of the galaxy. So the halo of the galaxy is like the sort of spherical-ish region in which the disk of the galaxy exists.
Right.
And there are stars in the halo of the galaxy. So you can define the halo of the galaxy by just things that are moving around sort of more in a sort of spherical blob than in the disk of the galaxy.
Right.
And so for a while we thought maybe they were like black holes or neutron stars or something that just isn't very bright.
Neutron stars, but no.
Sorry?
I love neutron stars. They're awesome.
Neutron stars are great. Black holes are great too.
Yes,
we've talked about both of these things in previous
because
iterations of our hangouts.
Hangouts are awesome. With us.
So if you're interested in black holes and neutron stars, you should go check our back catalog. Anyway, so the idea was that maybe the dark matter was just a bunch of those objects sort of circling around, and all of their mass added together gave you this extra gravity.
Right.
Right. So they were called. This idea was called massive compact halo objects, or MACHOs.
Yeah, because and one thing I find in astronomy is either they stretch to find some awesome, cute names, or they just do not get imaginative at all. Like, that's the Very Large Telescope over there. How big is it? It's very large. So I love that. And then you have things like dark matter and dark energy, which just confuse the crap out of people. So we have MACHOs, and what's going on with MACHOs, or what's not going on with MACHOs?
So right. So we don't think that MACHOs are the dark matter, and there are a couple of reasons for that, and I'll talk about those a little bit later. Okay. But basically, they come down to so we had some cool experiments to try to figure out if they were MACHOs, and they involved gravitational lensing, which we talked about last time. And gravitational lensing is where a massive object bends space-time, and you get this like dent in space-time, and then light follows a curved path around it. But also, if you have a really compact thing passing between you and a distant star, for instance, then the compact thing can kind of briefly magnify that distant object.
Right.
Just by like a lens can be a magnifying lens. It's kind of a similar thing happens. And so if you watch a really distant star and like a black hole passes between you and that star, you might see the star get a little bit brighter briefly. That's called microlensing. And so what we did was we got a bunch of telescopes, or a couple of telescopes, and we pointed them at like a star cluster in the distance. In this case, they looked at the Large and Small Magellanic Clouds, which are sort of satellite galaxies to the Milky Way, and they looked at the bulge of the galaxy, all the stars in the center of the galaxy, and just stared and looked for blips to see, if we did have all these black holes circling around like a beehive around in our galaxy, then we would see lots of blips as they passed in between us and those stars.
Right, that would make sense.
And we didn't see that many. So we can say that no more than about 10% of the mass in the halo is black holes, or
which
compact
is nowhere
objects.
Near enough what we need for seeing.
Yeah, not enough to be the dark matter.
Right.
So that's the MACHO story. And the alternative to MACHOs was WIMPs, and WIMPs stands
because of course, right?
Yeah,
why not?
Yeah, and WIMPs stands for Weakly Interacting Massive Particle. Okay, and so weakly interacting in this case means two things. It means doesn't interact very much, but it also means interacts via the weak force. So there's the forces of nature are gravity, electromagnetism, the weak force, and the strong nuclear force. Right. And so the weak force is responsible for things like nuclear decay. The strong force is responsible for holding, the quarks together in protons and neutrons, right, and holding like nuclei together. yeah, and you know what gravity and electromagnetism do. So the weak force, like, you can have stuff that interacts only through that, basically. And so we think that dark matter might interact just through the weak force. And so that's weakly interacting massive particles. Massive because it has mass, because it's matter.
Right.
And so that's kind of what we think dark matter is now. That's like our best sort of hypothesis for what dark matter is made of. And there are a number of possibilities for what this weakly interacting massive particle is. Some of them come from supersymmetry, which is a theory that it would take a while to go into.
Say that sounds like another series of hangouts we need to do.
Yeah, I think it would be. But so supersymmetry is like a sort of broader theory of the particles of nature and the forces, and in the theory of supersymmetry, you have a particle that could be the dark matter particle. You have a couple of options.
Right.
So, and there are weakly interacting massive particles in supersymmetry, so it might be one of those. So I want to talk a little bit about detection, ways to detect dark matter.
Right. So I mean, and so we talked a little bit too about how, you know, we were trying to detect machos by looking at that gravitational microlensing. We're not seeing enough of it out there. And then with WIMPs, with these weakly interacting massive particles, that really that do interact with the weak force, and obviously they have with the gravitational force because they have mass. How does one detect that?
Right. So detecting dark matter in terms of like confirming that it's there and where it is and how it's bunched up is a matter of looking for gravitational interactions of things, looking for how things move, looking for how light bends. But actually figuring out what the particle is, we kind of want to catch one, right?
Well, of course, yeah. That helps.
And that's hard because dark matter passes right through things. It doesn't do electromagnetism. But if it does the weak force, we can catch it in a similar way to the way we catch neutrinos. So neutrinos are also weakly interacting massive particles, actually. They have a little bit of mass, very little, and they only interact with the weak force. And we catch those by having a huge tank of water lined with photodetectors, and we wait for one of the neutrinos to smack into something in the water. And when that happens, it produces a little bit of light because it accelerates this thing through the water, and you get. That's a long story, which we could talk about another time. But with dark matter, there's a similar thing, which is that you take some kind of detector that has some kind of material, and you wait for the dark matter particle to come in and bounce against one of the nuclei in the detector, and that's called the nuclear recoil. It's just a nudge, like the dark matter particle might come and hit that. Scatter off one of those nuclei, and then that would either create a little vibration, or depending on how the detector is set up, you might get an ionization or might get some light coming from that bounce.
So on a subatomic level, it's just going, boop, and we're seeing something from it, right?
Yeah. And because it only interacts with the weak force, and because it's a very small probability of interaction, it's really, really rare to get one of these interactions, and so you have to wait a long time. You also have to put your detector underground because there are lots of cosmic rays coming down from space and coming through all the time, and you get all sorts of like muons and electrons and nuclei coming from space, all sorts of stuff. So if you put enough rock between the detector and space, you can shield a lot of that. So you can try and, you have to put it deep underground to get the shielding. And the same thing happens with neutrino detectors. You have to put neutrino detectors underground too.
And how far underground? Because I've heard just stupendously deep mine shafts going down.
Yeah, you put it in a mine generally. You want it around 2 kilometers, something like that.
Is that possible?
1
Hmm.
or 2 kilometers. You want it pretty deep. So,
Yeah.
like for neutrino detectors, the Super Kamiokande neutrino detector that I used to work at is one
I did not
kilometer
know that about
underground.
you.
Yes. So that's 1 kilometer underground. It's under a mountain. Um, there are mines so most of the dark matter detectors are in mines. Super Kamiokande is in a zinc mine. Um, in Australia, we're actually talking about putting a dark matter detector in a gold mine. Near Melbourne in Victoria, and
Oh, okay.
that gold mine is like 1.6 kilometers deep, something like that.
All right.
So you got to get it deep underground, and mines are good for that because they're usually pretty deep.
Right.
So, okay, so that's one way to find dark matter is to wait for it to bounce off of something in your detector. Um, I don't have a lot of time. I'll go very briefly into another way to find dark matter, which is through annihilation. So you've
That
probably heard
sounds
of,
pleasant. Sounds real
yeah.
pleasant.
So you've probably heard of matter antimatter annihilation.
Right.
It's how the spaceships on Star Trek are powered. Um,
So yes, I mean, come on.
uh,
Everyone watching this should at least have some general.
yeah,
If not, I think it's on Hulu now, Netflix, something like that. You
yeah,
can.
you can find it. So they take a bit of matter and a bit of antimatter and they collide them together. And what happens in when you collide matter and antimatter is those things annihilate and turn into basically pure energy.
Right.
So like if you take an electron and an anti-electron, which is called a positron, and you collide them together, then you get gamma rays, high energy light.
Right.
So with weakly interacting massive particles, for instance, the neutralino, which is one of the possibilities for what dark matter is if it's a supersymmetric particle, the neutralino is its own antiparticle, which is
It,
weird.
how does that work? So it's its own antiparticle.
Yeah,
I mean
yeah,
that's not. I mean I know quantum. People have difficulties with quantum mechanics
yeah.
and quantum theory, but being its own antiparticle just seems
It's weird,
like,
huh?
yeah,
Yeah,
it
it's
just seems
weird.
like, hey, unicorns.
Yeah, it's a strange thing, but it can happen, and I'm not going to go into all the details of it because that would take a while. But I mean, the only difference between an electron and a positron is that the electron is negatively charged and the positron is positively charged, but
Hmm.
otherwise they have basically the same particle, same properties.
Right.
And a neutralino has no charge because it doesn't do electromagnetism. Um, so it's not. It's there are ways that it can be its own antiparticle.
Okay. Well, okay. Yeah, I
So
can see that.
so if it's its own antiparticle, then you take one neutralino and you take another neutralino and you collide them together and they annihilate. And in this case, they don't annihilate to light, but they annihilate to other particles. And so you can look for signs of that annihilation by basically looking for places where you have a whole lot of dark matter together. And every once in a while, as the particles are buzzing around, there will be a direct hit that's close enough hit that it annihilates and you get other particles, and they get particles that you can see that are not dark matter particles. They're some kind of particles that we already know about.
So we'd be looking at places like galaxy clusters
Yeah.
and
So
things
you
like
look.
that, right? So where
Yeah.
massive, lots and lots of matter are already clumped together, where
Yes.
we are able to observe that the gravitational lensing anyway, right?
Yeah. So well, you want something nearby enough that whatever the signal is will be able to get to us, and you want something where there's a really high concentration of dark matter, really dense dark matter. So basically, we look at the galaxy center because
Hmm.
there's a lot of dark matter at the galactic center. It's more dense in the center than it is farther away, and we look at nearby small galaxies, dwarf galaxies they're called, and those tend to have a really high percentage of dark matter, and they're dense enough that we can look for signatures from that. And usually, what we look for is either gamma rays from annihilations of things that are produced by the dark matter, or we look for like high energy particles, or sometimes neutrinos. People have looked for signatures of annihilation through the neutrinos that would be produced during that annihilation event. So So there's like that. So that's called indirect detection. The
Right, because
thing
you're
where
not
you go
detecting it
down.
itself, you're detecting the signatures of something that might have caused those
Yes.
things to happen.
Yeah. Yeah. So with direct detection, we look for the actual particle itself bumping into something in our detector. With
Right.
indirect detection, we look for like the detritus, the aftermath of this annihilation event. And so we've seen a
Is that
number of.
similar how the Higgs was discovered as well? Is that we didn't detect it directly, but based off what we knew from it, we were able to go backwards to that and say, hey,
Yeah,
this is what was going on there.
sort of. So with the Higgs, we detected the decay products.
Right.
So we couldn't direct detect the Higgs, but the Higgs decayed really quickly within the detector, and so we detected a bunch of stuff coming out that was consistent with how a Higgs would decay into other particles.
Right. So do we have
So
anything like that to where we would know it would interact with in that way? Do we know what we're looking for indirect detection for that?
well, yeah, so it depends on what the dark matter particle is. So basically, the way things are now, there are a lot of suggestions of something that could be a sign of dark matter, but what it tends to be is we have an idea of the number of particles, the number of gamma rays, or whatever that should be produced by astrophysical objects we know about. And if
Hmm.
we see an excess somewhere, like let's say we see more gamma rays coming from the galactic center than we expected, we say, oh, maybe that's dark matter, and then we see if it's consistent with a model of dark matter and what that model of dark matter would look like. Or if we see too many cosmic rays coming from nearby, then we think like, oh, maybe maybe those cosmic rays were produced by dark matter annihilation, and then we figure out what kind of dark matter particle would annihilate to produce particles like that. And so there have been a couple of different like claims of detections of things that could be dark matter, but at the moment it's all pretty much like we see too much of something over here. Maybe it's dark matter. Maybe dark matter did it. And you know that's about what we can say at the moment because we
Right.
don't know what the particle is, so we don't have a clear like prediction for what the signatures of it should be.
So what because I know we are running a little bit short on time, but so I
Yeah,
did want to ask you one thing real quick before we do. We have a bunch of questions as
we have
always
tons of
because you
questions.
guys are
Yes,
awesome
yes,
for asking us questions. Um, so have we been able to at least rule some things out besides machos on because
yeah,
the biggest thing with science is that you can rule things out and help narrow down what
yeah,
the parameters what's going on. So have we been able
yeah,
to narrow that down a bit, or
yeah. We've ruled out tons of stuff.
so no space unicorns? That's not it.
Right,
Okay.
right. And we've ruled out things. We know that the dark matter isn't made of like just like dust or like brown dwarfs or like pieces of rock. Like we know that it's something fundamentally different. We know that it has to be a kind of particle that doesn't do electromagnetism, so it's not just like stuff that we can't see because it's dark. We know that it's actually visible.
Right.
So we've ruled out a bunch of things that are like regular matter, and I don't have time to talk about it right now, but I'd like to, which is like how we know that it's not regular matter. Like we have
Well, that
there
that I
basically,
think we've decided we're going to do that on the next episode, and I think
yeah,
we might just want to. I personally, and I'm sure you do too, on wanting to dedicate the entire episode in 2 weeks about the fact that we know it's not baryonic matter is what it's called,
yeah,
and and
and we know it's
going
real.
against Bond, going against that, and because I think it's
Yeah,
important to show that this is what we know of the universe, why we know it's this way, and
yeah,
why some theories, though they can be very profound and complex, just don't
yeah,
fit with the
yeah,
observation. So I think next episode, that's what we're
yeah,
going to fit on is why why it's not baryonic matter, normal matter that we
yeah,
that you and I play with every day,
yeah,
and about Mond. Do you want to tell people what Mond is besides
yeah,
some funky sounding name as a I guess a teaser before we get to the questions?
yeah. So MOND stands for Modified Newtonian Dynamics, and it's this idea that dark matter isn't really a thing. It's just that we've misunderstood gravity, and so if you believe that, there are people who believe that dark matter isn't real, but the reason we think it's there is because gravity is stronger than we thought it was, and gravity has different properties than we expected, and for a couple of reasons that really doesn't work. You really do have to have a fundamentally new thing. You have to have dark matter of some kind.
Right.
So we'll talk about that next time. One thing, just briefly, when you said, have we ruled things out? The reason I kind of smiled at that was that
have you ruled something out, Katie?
No, I haven't ruled things out, but
Okay.
but we've ruled out a number of things where we've also detected it. So like in direct detection, when we're trying to find, based on these underground labs, there are a bunch of experiments that have seen signals that they claim look like dark matter, and then other experiments have ruled those out, and the experiments don't agree. So we have this weird situation where there have been a number of detections, and they've all been ruled out by their experiments. And so it's like this really complicated situation.
I'm telling you, space unicorns. It's gotta be space unicorns.
It's probably space unicorns, actually.
Yeah. And so when that happens, I mean,
yeah.
I will gladly share my Nobel with you.
Okay.
So right. I'm going to go ahead and hit to the questions here.
Okay.
I don't have time to translate those that are not in English. I'm sorry. I didn't have time to get that all open, take a look at it. But I will try to get to them here. One here from, pull this up here, looks like from Steve Harvey. Is dark matter likely to be distributed evenly throughout the universe?
No, so it's definitely not distributed evenly. Because dark matter has gravity, it comes together via gravitational attraction, and so it clumps in places, and it has higher gravity, and then more of it's pulled in, and it also is attracted to regular matter. So places where regular matter is very clumpy, dark matter also comes into that. So there's much more dark matter than regular matter. So usually the regular matter comes into where the dark matter is. But it's definitely not evenly distributed. So like in our galaxy, it's much more dense at the center, and it gets less dense on the outside. And then throughout the universe, it's distributed in like clusters and filaments in this sort of cosmic web that's definitely not sort of uniform.
Right. Because if it was uniform, if it was just homogeneous, everything everywhere, we would not be seeing this clumping. So. But no, this is actually a really good question here. Let me see here. I'm not too sure about the context of the question, but I think it's just more asking about the detection method. So, cannot special radiation causes variations upon your readings? And I think that just goes into any sort of scientific detection, which is why you guys are trying to rule out things by putting it 2 kilometers underground, right?
So like, it's kind of funny with these detectors. One of the things you have to worry about is, let's say you have your mine, and your mine is deep underground. If there is radioactivity, like if there are radioactive decays in the particles of the rock that your mine is made of, like the walls of your mine, then that radioactivity from the walls can cause events in your detector that might confuse you. So you have to account for all that as background, and you have to be really careful that you have really good radiation shielding. So like the whole thing is like, it's like a needle in a haystack thing. There's all sorts of things that can make something in your detector go bump, and you really have to work really hard to distinguish those things from something that could be actually dark matter.
No, and let's see here. This is another one here from Bill. This is cannot a large gravity field bend light to such a point that it makes it look like a black hole? So I think that's more, when we're talking about large gravity fields, that we're talking about a large amount of mass, and once you have so much mass, it gets to that point where if you have that much mass and it's compact down that far, that's when you do get a black hole.
Yeah, so I mean, so gravity just comes from the amount of mass you have and how close you are to it. And so if you have a really compact amount of mass, you can get really close to it, and then the gravitational field is stronger. And so light is bent more strongly around more compact things because there's a sort of higher gravitational field. And the bending of light depends on how much gravitational field you have. So if you get a lot of matter together, you can have strong gravity, and it makes it bend light quite a lot. But then that, if you have enough mass in a small enough space, then it will become a black hole.
Awesome. And one last question here,
Okay.
really quick and easy.
Okay.
Where are you? So I'm Scott Lewis. I am in Los Angeles, California, and it is 12:30 here on the 2nd of August. And Katie is in the future in Melbourne, Australia.
In the future. Yeah, it's 5:30 p.m. 5:35 in Melbourne, Australia. That's where I am, and the sun is just setting. So that's
very nice. The sun has not been up for a while, but that's how it is. Now, first of all, I want to thank all of you tonight. You guys have been great with your questions in there. I've been seeing a lot of tweets out there as well, so thank you for putting that up there. And I apologize for not getting the event up and promoted. I actually kind of forgot because I was partying with a bunch of my nerd friends.
You were partying. Yeah, you had stuff going on.
Hey, can you blame me? I was partying with people that do awesome stuff on another planet.
Yeah.
That's
yeah.
And they're your friends too. And actually, they told me to tell you hi.
That's very sweet.
Scott Maxwell in particular said, "Hey, Katie," and
who did? Sorry.
Scott Maxwell.
Okay, cool.
He said hi.
Awesome.
So again, everyone, thank you for watching. I will try to collect any more questions that are coming through here as the world turns. If you have some more questions going on with that, you guys do know what next week's or not next week, 2 weeks from today, our next episode is about. So if you have any questions about what baryonic matter means and why we know that dark matter is not that, and please try to limit the modified Newtonian. Let's just try to keep things in the realm of possibility. However, there are some genuine questions that people have, and I've no problems answering them in the least amount of snark possible, because I try to be nice sometimes. But
and I will try to answer questions as well. And you can find us both on Twitter.
Yes. So tell us about your Twitter, because you just you're like at 12,000 Twitter followers now? 12,556. Follow her if you haven't.
They just keep showing up. I don't know why.
Yeah.
So you can find me on Twitter. I am at AstroKatie on Twitter. You can also find me on Facebook at facebook.com/AstroKatie. I post there much less often than on Twitter, but you can have kind of longer conversations. I'm also on Google Plus at +KatieMack, and you can find my webpage at astrokatie.com.
Yes. And though I think you said you're going to be traveling for a bit, so it might be on and off. But seriously, like some of the best Twitter conversations I have ever have been with Katie here. So if you guys are interested in science and want to engage with that, plus many other people involved in science communication, get on the Twitter, follow us around. We will engage with you and talk your ear off about science. I'm Scientific Scott on Twitter as well. This has been on Space Fan News. We will be back again, in 2 weeks. Please feel free to subscribe. Give us a thumbs up if you like this. I know many of you guys have been asking lately too, where's Tony? What's been going on with episodes? Lots of things have been changing. We're trying to get things regulated. I will make a post on that later on our Google Plus page and our Tumblr and all that fun stuff. So I am going to wrap this up. Everyone, again, thank you. You have been amazing. Katie, as always, you are wonderful. Thank you for explaining all the science.
Thank you. It's fun. I enjoy it.
All right. Well, I will see you guys later, and have a great day, night, and keep
Bye.
looking up.